All right. Let's just explain the question one by one. First, we take a look at the first question. Actually, this is the question from the textbook 7.4. Okay, so yes, this is a continuous random variable has a probability density function like this. Okay, here C is a constant, so we need to find out the value of the constant C. Okay, this is the general property, right? Because we know for the PDF of continuous random variables, the area under the curve over the interval got to be 1. So based on that, we use calculus. That's how we get C equals 1/2. And then what is the moment estimate of theta? Because after we know the C, then we would know this PDF right here, right? This PDF right here. And then the moment estimate, the definition is, yes, because here we only have one parameter theta. So we only need one moment here. Of course, the first moment. We need to get what is the expected value of x. And then we know by the calculation, we know this is going to be theta divided by 3. Theta over 3. So the moment estimator is what? Replace the EX by X bar, and then replace the theta with theta hat. Okay, take a look. We still use this one, right? Because here is EX equals theta over 3. And here is X bar equals theta hat over 3. That's how we say, okay, theta 3 equals 3x bar. That's the moment estimator for theta. All right. And show that theta hat equals 3 times x bar is unbiased estimator for theta. You know, to be unbiased estimator, we need to show the expected value of this guy, right? And according to this guy, it's going to be the same as theta or not. Yeah, so that's the way to do it. So this question 2 and 3, part 2 and 3, we got to follow the definitions strictly, okay? So what is the moment estimator? Moment estimator, we just define the moment estimator as from the moments, right? For example, this is the moment. And what do we mean by unbiased estimator? Unbiased estimator means the expected value of this estimator is going to be the same thing as the target population parameter, okay? Expectation, okay? You could not say theta hat equals theta. This is not right because theta hat is a random variable, okay? And the theta is just one value, a constant. And we know for a random variable to equals a specific value as a continuous random variable, this probability is just 0, excuse me. Okay. Probability 0 in statistics means what? Means impossible. Okay. Here we need to find the MLE for theta when theta equals 2. Okay. Because why do I need to specify n equals 2 only here? Because I think this is something we could work. You know, if we just put, yeah, I could put n as 3, at 4, but that's a little too hard, okay? So first of all, for the likelihood function, right? N equals 2, that basically we just multiply this 2, right? This is the density function, right? For I goes from 1 to 2. So basically here is just what? 1/2 1 plus theta 1, theta x1 times 1/2 1 plus theta x2. Okay, that's the likelihood function, and then we take a log likelihood. That's how we get this guy. Okay, right? We have, yes, this one equals 1/2 square, and then 1 plus theta x1 and the 1 plus theta x2. That's how you take the log. That's how we get this one. And then first order condition, we take the derivative of the log likelihood function with respect to theta right here. That's how we get this one. Okay, so basically we just take the, remember as I said before, here theta is the what? Is the parameter. X1, X2 are what? Are constant. You know, you just treat them as known. Theta is unknown, is a variable. Okay, and then take the derivative for this lnx, right? lnx. If you take a derivative with respect to x, that's what you got as 1 over x. Okay. All right. By solving the above equation with theta as the unknown, we get MLE of theta as what? As this one. Okay. So that's the MLE for theta. Yeah, please make sure you got this kind of calculus, okay? Because I would say this is the minimum amount of the calculus we have to deal with for this kind of MLE case. All right. Now for question 7.45, yes, as I said, right, I make it a very detailed YouTube video about how to do the question number 1 and 2, okay? So please refer to this video. You know, if you, I think the video, yes, you hit here, you will get it right here. Okay. This is very nice. You know, the idea is like the, okay. So please go watch that video. Okay. So yes, I would say this is a very good practice of MLE. Of course, this would be the hardest one we can come up with, I guess. You know, remember in the example we're talking about geometry, we talk about normal, we're talking about exponential, but this Weibull distribution, right? We never touch that. That's why I put in the homework. All right, for the last part, what complications are involved? This kind of two equation in part 2. You see here, after we get a beta and a delta, you see why this one is very hard to solve, because for delta is okay, right? As long as we know beta, then delta should be okay, because beta is an expression of, delta is an expression of beta. But for beta, take a look. This is very complicated, because first of all is what? Beta goes to the denominator, okay? This is 1 over, because this is inverse, okay? Is negative 1 power. That's the inverse. And also, the beta goes to the exponent of xi, okay? And on the other hand, on the left-hand side, just the beta. So beta itself is kind of linear, but the beta in the exponent is not linear, okay? That's why it makes to figure out what is the value for beta so complicated, okay? We have to use so-called numerical iteration to get this so-called analytical solutions. Okay, yes, I found that this article is very useful if you really want to know more details about how to get the solution. Okay, this is the one. Okay, please check out this article. All right. For the 7.46, this question, yes, this is kind of like a continued version of what? Uniform distribution over the interval 0 to a, right? Recall the MLE of a, we did it in the example, is the max of x1, x2, xm. So first we need to argue intuitively why this a hat, right? This MLE estimator cannot be a unbiased estimator for a. Okay, so remember, for this joint distribution to be non-zero, right? Because we know each of these xi has to be strictly between 0 and a, right? So yes, this density function is what? Is 1 over a if x, between 0 and a over this interval. Otherwise, it's going to be what? 0, right? So now we have x1, x2, xn. So the joint distribution for this x1, x2, xn is going to be every xi has to be 0 and a. That's why, those x1, x2, xn, everyone has to be less than a. Then the max of those n values should still be what? Less than a. So this one cannot be, if you take the expected value of that, right, cannot be a. Does that make sense? So it seems like a hat is always going to be less than a. So if you take the expected value of a hat, that should be less than or equal to a also. Okay, this is one way to intuitively argue this a hat could not be a unbiased estimator for a. There's another one you can see. Take a look. There's another example to work with here. Think about what kind of unbiased estimator for mean, for example, is the sample mean, right? But how we're going to take the sample mean? Sample mean is what? Is you add all those xi's together and then divided by n. So this is kind of like what? Some of the values are big, some of the values are small. Well, whatever. You just add them all together and divide by n. So this kind of average out effect will what? Will smooth the bigger values and small values, right? Kind of pick it between. But think about this guy here. Take the max. Always take the max. So this way, always focus on the extreme values. So this kind of estimation method couldn't get a what? Get an unbiased estimator. Unbiased estimator is kind of is what? Not too big, not too small. It's kind of like a between. This kind of average out effect. All right. Anyway, so for the part 2, we have to show this one. Okay, this one we're gonna show it later, but now we just use it directly. So we say if we know expected value of a hat equals na divided by n plus 1. Obviously, this is not a, right? Is it reasonable that a hat consistently underestimate a? Here, yes. Take a look, right? Because this one, n over n plus 1, a, is always going to be less than a, right? Because our n, the smallest value of n is 1. If you take 1 in there, is 1/2. So 1/2 a, of course, less than 1/2 a because our a is greater than 0. But take a look at it right here. This bias is what? Is not that terrible, as especially when n goes to infinity. You see this bias what? Goes to 0. This kind of situation is very special, right? First of all, is biased. Okay, obviously is biased, right? Because your n, you're never gonna get a infinity, okay? Because in real life, your n is a number. As long as it's a finite number, then this bias is always not 0. But this is not a terrible problem. Why? Because if you get a large enough sample size, this bias is what? Is very small. So this is exactly what we mean by this kind of a shrinking bias, attenuation bias, this kind of effect. Okay. All right. For part 3, propose a unbiased estimator for a. Unbiased estimator for a, because we know, right? We can easily say this E hat A hat equals n over n plus 1 A. And then, of course, if we just flip a 1, this one in the front is going to be what? A, right? So this whole thing is going to be unbiased estimator. Okay, this whole thing is unbiased estimator. You know, this is the general trick, right? Because if you know the expected value of your estimator is like a function for A is unbiased, you can easily make some adjustment to make it what? Unbiased. Okay, right? You know this is biased, and then make some adjustment to make it as unbiased. Now you can see expected value of this whole thing is gonna be what? A is unbiased estimator. All right. So for part 4, the key here, we need to figure out the density function for y, right? Now y is the random variable, right? And then what is the density function, PDF? And we follow this idea here. So this is the CDF for y. This is how CDF is defined. You know, if you check the stuff in chapter 4, you know what this means, right? So this is the CDF, capital Fx. Of course, capital Fy here. And then we want to know the whole, yes, here should be the max of this one less than y here, okay? All right, since the max of the x1, x2, xn all less than y, then each individual has to be less than y also. That's why we have the multiplication, okay? So this is kind of like the joint probability problem, okay? Because the joint probability, because you know each is gonna be less than y. Xn less than y, okay? Now this is the joint probability, right? And then since x1, x2, xn are independent, so the joint probability is gonna be what? Equals the multiplication of each marginal probability. That's how we can multiply each of the marginal one, okay? So that's how we get what? Because this one, for each individual xi, it has a what? Uniform distribution, right? From 0 to a. So uniform distribution to get the probability is easy, from 0 to x, and then 1 over a dy. Yes, here you could use y here, okay? Because our variables use y just for. So that's why you get a y, right? But for each, so, and then, yes, this kind of like a g is for what? Is for x random variable. Okay, so we have gy, we have this kind of y over a, and then you have how many of them? You have to multiply n of them. That's how you get this guy here, okay? So in a word, this equation gives us the CDF for the random variable capital Y. Okay, with the CDF, how we're gonna get a PDF, this little fy for capital Y. That's exactly, you take the derivative of the CDF with respect to Y. That's how you get this guy, right? So from here, you proved the PDF for Y is exactly this one. Of course, here for any Y values between 0 and A. But otherwise, if Y is less than 0, then that's a 0. That's why you get this kind of form, okay? right? Is that, and then otherwise it's gonna be 0, right? Because you take the derivative of this guy, exactly got this number, okay? This one. All right. After we have the density function for y, then we can prove, we can show, right? This a hat, the maximum likelihood estimator for a is biased, because a hat is the same as the capital Y, right? Both are the max of xi. So here is the density function, and here is what? Y, okay? So that's the definition for the expected value of y, and then we use the calculus. That's how we got this guy here, So, right? So, and obviously the bias is the expected value of the y minus a, that's this one. So this is biased. So part 5 is kind of prove the claim we used in part 2, okay? Expected value of a hat equals na over n plus 1. Okay. All right. Part 6. What is the a tilde? The moment estimator for a. Moment estimator, because we know now we're back to distribution for x. Because the expected value of xi is going to be a over 2, right? This is because xi, as I said, this is the uniform from 0 to a. So the expected value is exactly the center, right? The middle point from 0 to a. That is a over 2. Now you replace the expected value with x bar and replace the a with a tilde. That's how you say the moment estimator for a is what? 2 times x bar. Okay. Now suppose here we have how many unbiased estimator? First is this what? A tilde, the moment estimator. And the second is what? A chart. A chart here, yes, it's kind of adjusted what? MLE, because MLE is what? Is a hat. But we know MLE is biased. So we'll make an adjustment to make it what? Unbiased. So both are unbiased right here. Okay, a tilde and a chart, both are unbiased. And then which one is better? Of course, if both are unbiased, then we need to check what? The variance, the second moment. So that's why I put a bonus here, because think about the variance definition. First we need to know the variance of a chart. So we take this one out, the variance of a hat, and then this is the density function for a hat, right? This is the definition for variance. Y minus the expected value of y squared. Okay, this integral is a little complicated. That's why I give you this much detail here. All right. So finally we got, so the variance of the hat, this is exactly the variance of a hat, okay? Okay, this part. Right. Okay, and then we got this one. That's why the whole thing, the variance of a chart, you have to multiply this one with the variance of a hat. That's finally you get this guy. Okay, yeah, it's a little complicated, but for the moment estimator a tilde, the expected value is what? Is a, unbiased, no problem. But the variance of this one is much easier, okay? Because we tilde equals a tilde equals 2 times x bar. You take the 2 out, becomes 4, and then the variance of x bar. Variance of x bar actually is 1 over n variance of xi. What is variance of xi? Okay, this is a typo. Variance of xi, because xi is uniform, it's going to be 12, the a squared divided by 12. Okay, so this is a squared divided by 12. That's how we got this guy, right? 4 over n times a squared divided by 12. You got this cancelled as 3. That's how you got 1 over 3 n a squared. And obviously, you know, this one is always going to be less than that, because think about it, n equals 3, they're equal, right? But if n gets bigger than 1, then this one is always going to be bigger than this one, because n times n plus 2 is always going to be greater than n for any n greater than 1. Okay, so now we say both a chart and a tutor are unbiased, but a chart has a what? Smaller variance. That's why we say a chart is unbiased, but it has a smaller variance than a tutor. Of course, here a chart is better than a tutor. Okay, that's the conclusion. All right, and for the last question because for the example 7.11, we have these two results, right? MLE for mu is the sample mean. MLE for sigma square is 1 over square division of xi from the mean, right? But note, this is not equal to sample variance, because sample variance is defined as what? 1 over n minus 1, okay? All right, here you do not need to prove, okay? You can just use this result directly, okay? But in the exam, I may ask you to prove, but this homework you don't need to. You can just use this one directly. All right, after we know this one, and then in our case, what are the xi's? Our xi's are those one, x1, x2, x3, right? How many? Up to x what? 24, because in our case n is 24. We have 24 observations, right? How can for the maximum estimate for mu is just add these 24 numbers together, divided by 24. That's how you get this number, right? Because from our code. And then how can estimate for the sigma square? We by this formula, because we know this x bar is about 423, right? Something. And then each of the individual xi's, you use this 423 to subtract each of these 24 numbers, and then square the division, add them together, divided by 24. That's how we calculate it as this number. This is exactly, you know, this variance hat, you see this formula right there, okay? There's a catch. If we use this R code variance of A, this variance of A exactly, they do what? They did for 1 over n, this guy, okay? They're different. I hope this video will help you to understand this homework. And if you have any questions, please let me know. Thanks for watching. Bye.